Hello, and thanks for joining us today. Please take this opportunity to adjust your speakers and monitor as necessary to best view the presentation. I'm Rebecca Joan Brown, and I'll be leading you through the first part of today's webinar. We'll be discussing outdoor water efficiency and looking at some of the strategies that you can employ to make your projects more water efficient. We will be going through some calculations, so please have the materials we sent you ready. Feel free to play along by answering the quiz questions sprinkled throughout the presentation, but remember that you will need to take the quiz on your on-demand main menu in order to receive credit unless you also attended our live session. This course is designed as an introduction to water-efficient strategies and technologies. We will be looking at what these strategies involve and weighing their benefits and costs. In doing so, with both efficiency and conservation measures. We will look at the water efficiency credits in the LEED rating system BD+C and O+M and determine how the strategies we highlight can help you earn them. In order to help you understand what is required for LEED documentation, we will be guiding you through some sample calculations that would be used to demonstrate compliance. We hope that this course will help you to understand the drivers behind water efficiency and develop strategies to make your projects more water efficient. You will be able to identify LEED credits associated with outdoor water efficiency and perform the calculations necessary to demonstrate compliance to these criteria. In Section 1, we will look at the principles and drivers of water efficiency and look at water usage statistics. Then we will go more in depth with the LEED rating system to show you what credits deal with our water issues and what it takes to earn them. We will follow this with a focus on water usage and strategies for efficiency. Landscaping serves several purposes. It provides curb appeal for the project as well as a habitat for local flora and fauna. Some landscaping applications can also provide a retreat for building occupants, perhaps encouraging them to spend more time outdoors on their breaks. Site-adaptive landscaping is the practice of using plants that are adapted to local site conditions. Some of the factors to consider when choosing plants are the amount of rainfall for a particular region, the local climate, and the soil type and quality. Generally, native plants will thrive best. However, the use of plants from similar climates can also be effective. The practice of xeriscaping involves selecting climate-adaptive and drought-tolerant plant species, which can reduce landscape water by 50 to 75%. Drought-tolerant does not mean that plants do not need water, but they do require less and are generally very easy to maintain. In addition, xeriscaping also provides natural habitat and pays back over time due to less demand for water, fertilizers, and pesticides. Xeriscaping can also involve the use of non-vegetative landscaping, such as rockscapes or dry landscape gardens. One of the important factors to be considered before deciding on plants is a detailed soil analysis. Many local agencies compile and maintain a list of native plants in their area. There's a list provided here for the state of Texas, but you can find these types of lists for any state or area. Turf grass requires a lot more water to survive than many native plants and species. Minimizing the amount of site covered by turf is a strategy many projects use to reduce potable water consumption for landscape irrigation. If minimizing turf is not an option, techniques such as alternative mowing and mulching help reduce water consumption. Alternative mowing leaves the grass clippings on the ground as mulch. There are some mowers that will even divert the clippings down to ground level rather than leaving them on top of the grass. You might also consider contouring to direct rainwater runoff through the site, giving vegetation an additional water supply. This option would be more expensive initially, but could reduce the amount of water used and make the landscape more visually interesting. Trees provide a lot of benefits, both to a project and to the surrounding area. They clean the air of CO2, provide privacy to second and third floor windows, and are generally relaxing to look at. Plants growing in shade generally require less water and their soil remains moister. Large canopies offer a refuge for smaller animals and provide a measurable reduction in heat island effect. Water-efficient irrigation is just as important as the type of landscape used. Efficient irrigation is critical to achieving water efficiency credits for both BD+C and O+M projects. Traditional sprinkler systems have low irrigation efficiencies, but their operation may be improved by effective landscape and sprinkler design. Assuming an effective landscape design, the engineer designing the sprinkler system should use landscape zones to determine the placement of sprinkler heads, provide optimum application rate based on soil type, and avoid overspray to adjacent areas. Application rate is the rate at which soil is irrigated in inches per hour. If the application rate is more than the infiltration rate of the soil, runoff occurs. Programmable sprinkler systems are better than traditional systems because they can be programmed according to landscape zones, plant varieties, and schedule of operation. For existing building projects, check sprinkler operations on a regular basis to detect any leaks or malfunctions. Retrofit existing sprinkler heads with high-efficiency ones to minimize water waste and for more uniform water distribution. High-efficiency sprinkler heads can include rotary heads, mist, and micromist types. Rainwater can be used without treatment for landscape irrigation purposes since it is free of harmful minerals and salt. Apart from conserving water, the process of rainwater harvesting reduces surface runoff, preventing soil erosion, flooding, and minimizing the contamination of surface water with contaminants and fertilizers. Rainwater harvesting systems can range from a simple barrel, such as the one shown here, to multiple cisterns. Cisterns may be underground or above ground with pumps and controls. Some of the things to evaluate before deciding on a rainwater harvesting system are how much rain you plan to receive and for how long, and the area of the catchment building. This will help you appropriately size the collection tank or cistern. Rainwater collection and distribution systems can be included in new and existing construction projects after performing and analyzing installation costs versus proposed savings. The simplest formula to quantify the amount of rainwater a site will accumulate in a year is the area of the catchment times rainfall in inches per year divided by 12 gives you rainwater in cubic feet per year. Multiplying this by 7.43 will give the quantity in gallons. This will give you the maximum amount of rainfall a project may get, not considering losses due to evaporation. The size of the cistern should be decided based on peak rainfall during one or multiple years, the amount of time between rainfalls, and irrigation demand. The link on this slide will take you to one of the various rainfall calculators found on the internet. If projects utilize rainwater for indoor water applications, such as flushing toilets or urinals, it will contribute towards indoor water use reduction credits as well. From the rainwater harvesting system at Few and Evans, the architects moved on to combine this technology with recycled gray water at the 5-story Longstreet Means Hall. This is the first hall on Emory's campus to harvest gray water for toilet flushing. The gray water reclamation is projected to save more than 1 million gallons of potable water per year. The project system recycles wastewater from all sinks, showers, bathtubs, and laundry facilities for use in flushing toilets. The system generates 12,486 gallons of gray water per day, and because the volume of the gray water generated is so much higher than the demand for toilet flushing, the university plans to connect this system to future residence halls in the vicinity. This linkage can maximize the return on investment for the system's tanks, filtration systems, and controls.